Now, the second problem is interesting because it's not entirely clear that the same dynamical situation could give rise as a solution to both a circular motion and also a harmonic motion, but gravity does. Okay, this 1 over r squared does. There are a lot of very nice properties of 1 over r squared. And in fact, if you take orbit at the surface of the Earth, radius r, and you also at the same time let somebody draw through this tunnel, you can solve for the tunnel motion and you can see right away that it's harmonic motion, right? And also the period will be exactly the same as this orbit. So it goes like this, okay? Now, the world line of a circularly orbiting particle is obviously a helix. It's just going like this, okay? The world line of this particle is obviously r of t is simply a sine wave, okay? And the world line for the other particle is whatever, x to the 2/3, some like a parabola kind of thing. Now, there's just, if you look at the projection, take a helix, all right? So this is r of t for an any orbiting particle, the Earth around the Sun, the Moon around the Earth, etc. All right? So basically, this is the world line, okay? So this is the world line of a particle. This is the time axis, all right? This is the xy, all right? So r is simply along here. At any point along the time axis, the distance in the xy plane is the same. Okay, so we just call it r, which is x squared plus y squared square root. Now, this, if you look at it over here, is just a circle, okay, in this projection. If you collapse this down, project it onto the xy plane, it's simply a circular orbit. Stretch it out along the t-axis, and you get a helix. And if you look at it along this axis, you can see a sine wave, okay? If you project this, if you had a light casting a shadow on a page over here, right, you would see just a sine wave. All right, so it's the same solution. You have a circle, a helix, and a sine wave.